Now, its simple means is basically half-life, the term which is used for radioactive materials. Every time the radioactive materials are becoming decay, or you can say they are decayed and decayed and decayed and decayed. So problem is started that how much material is left behind after a certain time. It's very difficult to actually keep an eye on. You can't keep an eye on a material for like each and every second, each and every minute. It's difficult, right? So what we have done, we have just make a small calculation, or you can say a small term that is called half life. We just see, okay, let's suppose if you have a material of radioactive material, let's suppose, let me give you an example. You got a material of 25 grams, let's suppose uranium. Now we will check only that what time it will take to reduce the 25 grams of material to 12.5 grams. That's it. So that time period will be considered as a half-life. So here the definition of half-life is written. I want you to write it down. Half-life can be measured, can be the measurement of the decay. The half-life of a radioactive isotope can help us measure radioactive decay of a substance. And what is the definition? The time it takes for a number of nuclei of isotopes in a sample to half. Now there is another small definition for that as well. The time it takes for the count rate from a sample containing the isotopes to fall to half of its initial level. What is that thing called count rate or activity? Yes, Manu. What is that thing called count rate or activity or whatever?
Like the radioactivity of the substance?
You can simply say that, for example, if you have 50 grams of material, the activity or you can say the count rate, the number of atoms are decayed will be more, right? But if it's reduced to 25 grams, the activity in which the radioactive materials converted into further decay, I mean, the further decay take place will be less. So as the activity goes, I mean, as the what you can say radioactive material become halfer and halfer, the count rate, or you can say the activity in which radioactive elements converted into half of its quantity will be lesser and lesser and lesser and lesser. One time it will come that it will be very slow, very less. Initially, it will be very fast. Count rate will be very fast. And count rate will be measured in form of BQ. The unit of count rate is BQ. So this is another definition in the form of BQ. So that is what we called as half-life. Now, a very interesting fact. Let's suppose you got this graph. Let me just enhance it if it's possible for me. Now you can see this graph, right? It's a graph between time taken or time in year and a graph of count rate in accounts. Now, how will you find out what is the half-life of that particular material?
You take starting value and divide it by 2.
So basically, initially you have total number of atoms 200. You will check in what time that 200 atoms will be reduced to 100. So check it out. This is your 100. So draw a straight line here, here, here. This is the point where it reduces to half. So it is nearly 5 or will be 5.1, 5.2. So half-life of this particular material whose graph is shown here is 5.2 or 5 years. All right. Now check this out. That was a material actually. So what is the half-life of cobalt-60? To find the half-life of cobalt-60, we need to know the definition of half-life, which we already know. Half-life is the amount of time taken for half of the nuclei in the sample to decay, or for the count rate to half. On this graph, it's all story what we already discussed, we already seen. This is discussed over here. They have shown you how they did it. Now this is interesting. I want you to write it, please. The initial activity of a sample is 350 BQ. What is the final activity as the percentage of the initial activity after 2 years? Yes, Manu, did you copy?
Yes, sir.
Okay. Now let's see the thinking of this. Take it as the number of atoms or anything, but it's BQ, so you treat it as the same. The formula is very simple. You divide it, two half-lives means you have to divide the BQs how many times? Two times, right? So number of, what is it? Uh, Activity left after one half-life. How will you find out, Manu? Simply 350 divided by 2, which is equal to how much? 175 BQ.
Yes.
And number of activity left after second half-life. It will be 1 upon 75 divided by 2, which is equal to how much?
87.5.
87.5 BQ. Now, what is they asking? What is the final activity as a percentage of the initial activity after 2 hours? So basically, 87.5 divided by 350 multiplied by 100. So what is it?
25%.
So it means that, what does it tell you actually? It tells you that after two half-lives, the material or the activity left behind will be 25% of the actual activities. That tells you this. So 75% of the material is decayed or will form into some other new material. Only 25% of the material left behind. That's what it means. Let's move on then. Now check this out. How did they actually solve it? 25%. Now, some questions related to half-life. Now, this is interesting. You know, you keep on dividing by 2, dividing by 2, dividing by 2. If there are two half-lives, that's fine. You divide 2 times. But what if you have 5 half-lives or 10 half-lives? Will you keep dividing it by 2? So we will have a formula. Amount divided by, rather than 2, we will put 2 to the power number of half-lives, and that is equal to amount left. This is the formula we will be using. Now, how will we be using? Let's see it.
Sir, I've written it down.
Which what? Yes, Manu, what are you saying? Hello?
I'm doing the question.
Okay, okay. So did you write it?
Yes, yeah.
Okay, try this first. First, you try. An isotope of cesium has a half-life of 30 years. If 1 gram of cesium 137 disintegrates over a period of 90 years, how many grams of cesium 137 would remain? How did you solve it?
I did 1 divided by 2 to the power of 3.
Okay, that's simple question. So you have done absolutely right. Now there are different versions coming in this question. Check it out. This one is absolutely right. 0.125. Now check this one. Selenium 83 has a half-life of 25 minutes. How many minutes would it take for 10 grams, 10 milligrams of sample to decay and only have 1.25 milligram of it remains? Now everything is given, but they are asking you the total time. How will you solve it now?
It will be 3 half-lives, so 25 times 3, which is 75.
Yes, absolutely right. So every time you have to use this above formula by some way or another, and you can have, in this case, it's 75 directly. Very simple. But by the way, good. 75 minutes. Can you try this? Where is it? Try this. How long does it take 100-gram sample of AS81 with a half-life of 33 seconds to decay to 6?
Sir, I don't understand.
No problem. Let's check it out. If you write the data, it will be easy. How long it takes 100 grams of sample. So this is the amount which is given. So amount is given as 100 grams with a half-life. Now half-life is given 33 seconds to decay to this. So amount left 6.25. Use this formula. What are the things which are known to you? You know amount left. So why not you find out the total number of half-lives? So let's do that. 2 into number of half-lives is equal to amount divided by amount left. So what is the amount? 100 grams divided by 6.25. What is the value coming up?
16.
16. So 2 number of half-lives is equal to 16, right? Now can I do it like this? Number of half-lives 2 raised to the power 4. Can I do it like this?
Yeah.
So how many half-lives actually passed?
4.
4. If one half-life is 33 seconds, how many of 4?
132.
130. So your answer is 130. Now you understand it?
Yeah.
Sometime you have to multiply, sometime you have to divide it as well. It's all how you do it actually. There are further questions. You will inshallah understand this topic fully. I'm rubbing the formula as well, so you just check. Okay, try that question. What is the, now this is a bit other way around question. What is the half-life of a radioactive isotope if a 500-gram sample decayed to 62.5 grams in 24.3 hours? They are asking you to find out the half-life.
I got 12.15.
I don't think so. It's not even the option present in this, but let's see. No, it is not there, and the answer was 8.1. Now, how was it? Let's see. You have to find the half-life, right? The question is 500-gram sample is decayed into 62.5 sample, which is equal to 2 is equal to number of half-lives. 5 divided by 62.5 is how much?
8.
8. So it means that 2n is equal to 8. So I can write it down 2 raised to power 3. Can I write it?
Yes.
So n is equal to 3. So it means there are 3 half-lives. So 24.3 means 3 half-life. So how much is 1 half-life? 24 by 3 divided by 3, which is equal to how much?
8.1.
So remember that when you have to find out the half-life, you have to divide it. When you have to find out the total number of years, you have to multiply it. All right, Manu?
Yes.
Okay. Let's solve some more questions so that your concept will be further clear. What is the half-life of plutonium 214 if after 820 seconds, a 1 gram sample decayed to 0.03125 grams?
I got 164.
You go 164. Let's try. Oh, where is it gone? Yeah, 164. Absolutely right. So now you understood it, right? Now another one. Manu, do you have fission and fusion in your course as well or not?
We do.
You do have it. Okay. And I think we better discuss that after that as well. But do you understand this half-life fully? Because this is complete numerical things and everything included with that. Nothing is extra other than that will come in your examination.
Yeah. I got 12.5.
12.5. Now put a heading, nuclear fission reaction. It is written GCSE. Don't worry about this. This is not related to that. Definitely there will be something extra in that. It's just written it. Now, first of all, you tell me what is meant by nuclear fission reaction.
It's splitting of a nucleus into small nuclei.
So basically splitting of a big nucleus into a smaller nucleus. Now point is, you think it's only uranium that is used for this purpose, or is there something else can be used for that purpose?
I'm not sure, but we do use other things.
Remember that uranium is very lessly, you can say, found material. You can't use it, or you can't use it in, initially it was a thinking that uranium can be used, but the problem with the uranium is not omnipresent. You can't find it so often. So that is the reason with uranium, you can also use plutonium. Plutonium. I don't know the spelling exactly, but that material is also used for the purpose of, uh, just a minute, let me just check it out. The plutonium is also used for the reason, yes, plutonium. So plutonium, sorry. So word is actually plutonium. That is Plutonium. Plutonium got a atomic number 94. That material is much more better. I mean, you can found it easily rather than the uranium. So this plutonium also used for the purpose of nuclear fission reaction as well. But mostly in the books and everywhere you will find mostly uranium 92 235. The most famous one is this one. Okay. So I want you to write few lines on this. In nuclear fission reaction, a large unstable nucleus broken down into two smaller particles. Two smaller particles. For example, uranium 235, which is a naturally occurring isotope of uranium, is broken down into two smaller particles, barium and krypton. Barium and krypton. Barium and krypton. Another element named plutonium, PO, atomic number 94 is also used to perform nuclear fission reaction. Now, how do we perform this reaction, Mahnur? What do you think? It will performed, or it is like spontaneous reaction which occurs itself, or do we actually need to do something to perform this reaction? Yes, Mahnur, what do you say?
I'm not sure.
Remember that in some radioactive materials, this type of reaction occurs simultaneously, or you can say spontaneously. But remember that that is very rare to see. So actually, to actually see this nuclear fission reaction, you have to perform something. Now, what do you need to perform? I will also explain it to you why we do that. Initially, what scientists were thinking, they were thinking that they will bombard, let's suppose, proton on a nuclear uh, radioactive material like uranium. As soon as they bombard this proton, it won't hit. The reason is in uranium, you got protons as well. So proton and proton or positive charge actually repel each other. So actually it didn't hit and will not give us the proper result. Then they think, let's try with the electron. They try to bombard the electron onto the radioactive material. Again, some electrons are already there. They start repelling it. Some electrons are hit as well, but didn't get the proper result. Now they think of bombarding it with a neutron. Now neutron has no charge, so positive or negative charges do not attract or repel each other. Neutrons slowly go into the material and it hits the nucleus. Once it hits the nucleus, we found out that we actually got our result. We have done this reaction so that we actually need to have extra amount of energy which can be used at so many places. That energy which is actually emitted during this nuclear fission reaction can be used for so many purposes. That energy can be used to make electricity. That energy can be used for the weaponry, atomic bomb and everything. But mostly, it is used to make electricity actually. So we do use that energy to make electricity. Remember that. So it's a very simple process, which is written over here. Nucleus now, first of all, remember that the unstable nucleus, now we will simply bombard the neutron onto an unstable nucleus of the radioactive isotopes of uranium or plutonium, whatever you're using. As soon as it absorbs neutron, in the first step, it's broken down into two of its daughter nucleus. One will be krypton and the other will be barium. Along with that, lots of energy is released. Now, what is that energy? Gamma rays are emitted. Plus, you will have three extra neutrons which are emitted out. So, I want you to write it first. Process of nuclear fission reaction, put a heading. A radioactive material will be bombarded by a neutron, by the neutron. Continue. The nucleus of a radioactive element, the nucleus of radioactive element absorbs a neutron. Second bullet point, absorb the neutron. The nucleus splits into two daughter nucleus, into two daughter nuclei. The radioactive nucleus splits into two daughter nuclei, and also energy is released, and also energy is released through this fission reaction, through this fission. Next, the nucleus will also emit two or three high energy neutrons, during the fission reaction, along with two or three neutrons, gamma rays are also emitted. Now, technically speaking, this is the reaction. Don't copy this. Just I want to show you something in that. Check this out. You got this one neutron, right? And this is your uranium-235. This neutron is absorbed by uranium-235 and it becomes 236. Here, this is your atomic number, or in other words, this is your proton number. And the above one is your nucleon number. So as soon as 235 become 236, it become unstable. And it will broken down into two of its constituents. One is called barium 56144 and the other one is krypton 3689. Remember that these two are also radioactive materials. Along with that, you will have these three fast moving neutrons and lots of energy is released. Now I have written here is this is an exothermic reaction. Manur, what is meant by exothermic reaction?
It releases energy.
Remember one thing, every single reaction, whatever occur, whether it's a fusion reaction or a fission reaction, both release energy. Important thing is that input energy will be less than the output energy, or you can see the energy released as an output during this reaction will be more than the energy given to this reaction. If this will be the case, that type of reaction will be called as exothermic. So what is exothermic reaction?
Yes.
In which output energy release will be more than the input energy given. So remember that this reaction is an exothermic reaction in which more output energy is released rather than, as compared to the input energy given to it. Right? So if you just check it out, you are only providing one neutron. That's it. And as a result, you are getting three further neutrons. Now, I ask you one thing. What do you think these further three neutrons, what they will do? They will further go to some other uranium nucleus and again release three neutrons. So one each neutron will release three further neutrons, or you can say these three neutrons will further release nine further neutrons. Am I right?
Yes.
And same thing happens, it goes on and on and on and on and on. So actually, what did you do? You started with just one neutron, and that particular reaction started itself. And it will never finish until the whole material will finish. So we sometimes call this reaction as nuclear fission chain reaction. Why saying chain reaction? Because once you start that, you don't have to do anything. You have to just sit back and see it will automatically continue, continue, and continue. So this reaction is also called as nuclear fission chain reaction. Chain reaction is one incident happened with the other one, and it will continue and it will go on and on and on. Okay, I want you to write this equation, please. This is the equation of a nuclear fission reaction. If you see that one neutron bombard on 9235 uranium, and in the result you got krypton and barium. This is 56, this is 144. Along with that, you will get three neutrons and lots of energy will be released. Okay, if you really want to see this equation is 100% right or not, check the nucleon number on the left hand side and compare them with the right hand side. They both should be equal. 1 plus 235 will be equal to 236. Now check this out. 89 plus 144 is how much? Yes, Manu, how much are they? It's 100, and then you place 11 into that, it will be 200, and out of that, it will be 233 altogether. It's 233, 232, sorry. So it is 232, plus you got three neutrons. So 232 plus 3 will be equal to 230, 233 plus 3 will give you 236 on the right hand side and 236 on the left hand side. So both are right. Now check this out. 0 plus 92 is 92. Now check this out. 36 and 56 is how much? 90. Your left hand and your right hand equation is 101% balanced. So it means that it's a balanced equation of a fission reaction. Yes, Manu, shall we move?
Yes, sir.
Okay. Now, some more things related to that. What are the products of the fission reaction? That is important. Now, you tell me, Manur, what did you see? What are the products of this reaction? The first products are two products, which are krypton and barium. Second, gamma rays, which carries excess energy. And the last but not the least, neutrons that can start a chain reaction. So one by one, I want you to write in your own words what are the products you have seen in the equation. Can you quickly write it? And also write if they perform something. This is your equation. Now, what did you see? What is the first thing you write? What is the product of this reaction?
Krypton and barium.
Yeah. So these are the two products or products for this fission reaction. And what are the other byproducts of this?
2 to 3 neutrons and lots of energy.
Lots of energy. Lots of energy can be used for so many purposes, while three neutrons can further go into fission reaction and can perform a chain reaction. So write in your own words what are the products. And one more thing, because when you say lots of energy, remember that you're talking about the gamma rays with the excess amount of energy. Yes, Manu, have you written?
Yes, sir.
Okay. Now, once you understand everything, no issues at all. Now, nuclear fusion. What do you think nuclear fusion reaction will be?
2 small nuclei joining to
Yes.
form a larger nucleus.
Yes, you can simply say it's a name suggest as the name suggests fusion. Fusion means a fuse of two smaller nucleus into a bigger nucleus, right? So when you say so, it means you are fusing them together. So when you are fusing them together, it means fusion of two smaller nuclei to give you a bigger nucleus. Now you think of yourself, it's very difficult to fuse two smaller nucleus to give you a big nucleus. For that, lots of energy is required, right? So for this particular reaction that is called fusion, you need lots of energy, approximately 100 million centigrade degrees is required. That's it, which is not possible on this earth anyway. This reaction is actually happening on sun. Remember that. So for that, you need a very high pressure, very high temperature. Without this all, you can't perform this reaction here. So the point is, in this reaction, two hydrogen nuclei fuse to give you a helium nucleus. Now you think of yourself, two hydrogen nuclei are having electrostatic force and opposing force and everything. So to overcome those force and to actually fuse them together to form a helium nucleus, quite much energy is required. So what do you think this reaction would be? An exothermic or an endothermic reaction?
Exothermic.
It will be an endothermic reaction. Endothermic reaction in chemistry is a reaction in which you have to provide energy. Endothermic reaction. In this reaction, mass can be converted into energy as well, as E is equal to mc square given by Einstein. That is what it is written here. I want you to write this whole, please.
Yes, sir, I'm done.
Done. Okay. Any question related to that?
No, sir.
Simple. Okay. Now I want you to write this equation as well. That is its equation. Two hydrogen molecules, or you can say hydrogen nucleus. One is isotope and one is the simple one. They fuse together to form a helium nucleus. Manur, after finishing this, shall we jump on to the mechanics? What do you say?
Sure, sir.
Right. So once we finish with this topic, there are a few more topics left in that. Like we have equations, mass and anti-mass, and then we inshallah jump to mechanics because that was a topic which was actually pending in this particular thing. So we will finish that because we have to go back to our quantum phenomena once we finish with all this, right?
Yeah.
Okay. Just write the equation. Yes, Manu, did you copy that? Okay, now the conditions. As I just told you, for that, you need a very high temperature and very high pressure. And that makes that almost impossible to develop such kind of power station or of such kind of economically friendly power station on this earth for a fusion reaction. So very high temperature and high pressure can only be available on the sun and only sun. So I want you to write that, please.
Sir, I'm done.
You're done. So Manur, I think we better stop it here. I want you to go through this nuclear fission, fusion, and what else we done? I think we have done what? I forgot.
Alpha, beta, gamma.
Yeah, alpha, beta, gamma. I mean, today we have done half-life and nuclear fission and nuclear fusion reaction, right? So next
Yeah.
time, inshallah, Aziz, we will be doing some equations related to that and
Yeah.
further something if we have it in this particular topic. And then, inshallah, we will jump back to our mechanics topic. And after that, we will have materials. And then this particular unit is going to be finished and we will go back to our quantum mechanics. It will take some time, but inshallah, Aziz, with all everything, we will sort it out. And second thing is, after finishing with this, let's, I think, have some, let's start the practice for the past paper as well once this one is finished. Because we didn't do any practice, only doing questions and questions and questions. So what do you say? Once we finish this whole topic, I mean, I'm talking about whole unit, we'll do some practice as well for the past papers. You already sent it to me. So we will, inshallah, Aziz, uh, make arrangements to do the past paper practice as well. Okay? Then take care.
Yeah.
Okay, bye bye. Okay,
Yes, you
Manur,
too.
yeah, one more thing. Manur, when is the Eid at your place? I mean, where you live?
When is Eid? Shop. 10th.
10th means when?